Today we're looking at the graphs for exponential and logarithmic functions. Now, these two graphs are inverse functions of one another, which means that if you take one function and you just switch places with the x and the y, you get the other one. So, a basic exponential function is in the form y equals something to the power of x, where that something is positive. Now, here I've used 2 as an example. If I want to create the inverse function for this graph, and by the way, this graph looks like a basic sort of exponential like this. We've seen the shape of these before. They go through 1 here because anything raised to the power of 0 is 1. And then they go shooting up sharply over here because raising 2 to increasingly bigger powers just doubles it and doubles it and doubles it, so it gets big really fast. Now, if I switch places of the x and the y here, clearly I've made a different function. But we're not used to seeing functions written in this way. We're used to seeing them written in the form y equals something. And we can convert this into a different form. It'll still be the same graph, but it will just look different if we retell this as a log. So here we've got 2 to the power of y equals x. So I can write the same thing as 2 to the power of y equals x. Remember, we tell the story going around in a circle. And these two things are exactly the same as each other. They just look different. But they are both the inverse function of this one. Now we have y equals something. And more commonly we'll write the y first. Y equals the log of x with a base of 2. Now, inverse functions are reflections of each other around the line y equals x. And that's because really the x and the y are just swapped. So the line y equals x it goes through the origin and it has that 45-degree angle, a gradient of 1. So if we were going to reflect this curve around the axis, another attribute that we should have written on this one is the fact that it has an asymptote on the x-axis. It gets closer and closer to the x-axis as x gets really small, but it never actually reaches it. So when we flip this around here, what we get is one that has its asymptote on the y-axis and is shaped, goes through 1 here, and is shaped roughly like this. And it gets closer and closer and closer to the y-axis, but never actually touches it. And this is the graph of a basic log curve. Here we've got a log with a base of 2. Now, as you change this number from 2 to say 3, 4, 5, that just changes the fatness or the skinniness of the curve. It'll still have this same basic shape, and it'll still have the asymptote in the same place, and it will still have that same intercept. So now let's draw both of our basic graphs here. Now I've just used an example of each type. I've used y equals 2 to the power of x and y equals log of x with a base of 2, just because 2 is a nice simple number to use. And I've noted the main features of each of these graphs that we need to know. Now, let's look at the purple one first. Y equals 2 to the power of x. We know that as x gets smaller and smaller, it approaches y equals 0 but never actually reaches it. Now, why does this happen? Well, because as we raise 2 to a really small number, let's try a small one like, say, minus 100. When x is minus 100, what's y? Well, we know from our use of negative indices that what this really means is 1 over 2 to the power of 100. And 2 to the power of 100 is a really big number. So 1 divided by a really big number, that's a tiny, tiny fraction. Now you can see that as x gets smaller and smaller, this number on the bottom is going to continue to grow, but we're always going to have a 1 on the top. So we just get a tinier and tinier fraction as we go this way. On the other hand, as x gets really big, it's going to go shooting up really steeply. So the main features of this graph, its domain is all real x, because x can be anything in either direction. When x is really small, y will be a really small fraction, close to 0, and when x is really large, y will be ginormous. The range, that tells us which y values can we have. Well, we never get negative values of y, and that's because no matter what value of x we put in here, we only ever get a positive fraction. We never get a negative number out of it. So y has to be greater than 0. And that makes sense then that the asymptote is the line y equals 0, because y can never be 0. Now that line, we normally call it the x-axis, don't we? But it's also the line y equals 0. because y equals 0 for all of the points on that line. And the only intercept that this graph has is here at 0, 1. Why does it have an intercept there? Well, if we say let x equal 0 to find the y-intercept, then y equals 2 to the power of 0, and anything to the power of 0 is just 1. So we get that point 0, 1 right there. Now, when you're graphing this, the key points you need the asymptote, make a dotted line. You need this basic shape, and you need the intercept, but also one other point. Now, the reason you need another point, and it's up to you which point you choose, is because as this number changes, if we were to graph y equals, say, 3 to the power of x or 4 to the power of x, it changes how sort of fat or skinny this curve is. It still has the same basic shape. So, to lock in the scale and prove that we have actually graphed y equals 2 to the power of x, not some other exponential curve, we need at least one other point on the graph just to lock in that scale. So I always pick something nice and simple, like I let x equal 1, and I see what y would be by just plugging it into that formula. It would be 2 to the power of 1. And 2 to the power of 1 is just 2. So I know that when x is 1, y is 2, and that gives me that point 1, 2. So I can just lock that in, label it, and that's everything my graph needs. It's nice practice also to label the line when you draw it. Now let's look at the basic log function. We've seen that it's a reflection around the line y equals x because it's the inverse function of this one. So that means that instead of having an asymptote here, when we flip that, we get an asymptote along here. And as we approach that asymptote, we get closer and closer to it, but never reach, for the same reason that we never reach over here. So the basic features then of our log curve, x has to be greater than 0. Why is that? Well, we can't take the log of a negative number. X cannot be negative here. And the reason for that is if we're doing 2 to the power of something, you never do 2 to the power of something and get a negative. Just doesn't happen. This number can be positive, can be negative, can be a fraction, can be all sorts of things. You never get a negative number here. And so that explains why x can't be negative in this situation and why it's always on this side of the y-axis. The range, well, y can be anything you like because we can say 2 to the power of something and we can raise things to any power we want, and that's the y there. That's what we're doing. And that explains why all real y, we've got y values that are very, very small and y values that are going to go up to be very big. The asymptote is on the y-axis, and you need to draw that in with a dotted line. And we can also call the y-axis the line x equals 0. And we have an intercept at 1, 0. Now you'll notice the symmetry there with the other intercept being 0, 1. Why do we get the intercept there? Well, if we sub in x equals 1 here, then we're going to get this. 2 to the power of something is 1. 2 to the power of 0 is 1. So when x equals 1, y equals 0, and we get that point. Now, just as with the other graph, we need to lock in some other point to give us the scale of our graph. So here I've let x equal 2, subbing that in. When x equals 2, what's y? 2 to the power of something is 2, 2 to the power of 1 is 2. And that gives me that point 2, 1 that I can label. You can label any point you like, but I think that's a nice easy one because it's nice whole numbers that we can use.